Hey guys, so this is our last type of double replacement reactions, or double displacement, and it's called gas evolution reactions. And again, we're going to find ourselves like, how are we going to know it's double replacement? It's going to be two compounds reacting together, and we're going to see this happening. And there's essentially two types of gas evolution reactions. One in which one of our products is going to be a gas right off the bat. Others form something that we call an aqueous intermediate or an intermediate aqueous solution, which then spontaneously decomposes into a gas. So here's an example. First one, we have sulfuric acid reacting with lithium sulfate. So we might be quick to say this is an acid-base reaction, but remember, the qualification for an acid-base reaction is not only an acid, but also a base, okay? And lithium sulfate does not fit into the base definition for us because it doesn't have hydroxide ions, but we are treating it as double replacement as we do when two compounds react. So remember, the H plus ion is going with the sulfide and the lithium plus ion is going with the sulfate, so we need to form two new compounds. And here, right, it's the H plus ion with the S2 minus, so we get H2S, and then we get lithium sulfate, which is Li2SO4. And remember, one of our first two rules is all alkali metal compounds are aqueous, so that's why lithium sulfate is aqueous. And here, how do we know H2S is a gas? Well, that is one of the reactions where a gas forms right away. It is to be understood by us that H2S is a gas. Yes, that means that we need to memorize that. But in general, small, like light in terms of weight, molecular mass covalent compounds, so like lithium sulfide here, or hydrogen sulfide here is covalent because it's two nonmetals. I understand that we got them through ions, but it's okay. We're still thinking of it as covalent. And the mass is like 34. That's pretty light for a covalent compound. So light covalent compounds are going to be gases. So H2S is a gas. Now if we take this, so that's a finished balanced reaction, the lithium 2 on both sides, hydrogen 2 on both sides, sulfate and sulfide. Okay. So our next reaction is when you take sulfuric acid, right, H2SO4, and react it with sodium bicarbonate. And again, this is two compounds reacting together, and we are going to do a double replacement. So the H plus is now going to go with the HCO3 with the bicarbonate, and the sodium is going to go with the sulfate. So remember, neutral products are so important. So the sodium ion is a +1. The sulfate ion is -2. So we're going to get Na2SO4. And remember, alkali metals are always aqueous, so I know that Na2SO4 is going to be aqueous. And then I'm leaving it as HCO3. The reason I do that is just to hammer home the idea that this is a double replacement reaction, okay? Now, a compound that begins with an H and ends in aqueous, this is an acid, so we technically make carbonic acid. And if I want to balance this reaction, we need to make sure that I put a 2 in front of the sodium carbonate or bicarbonate to get two sodiums on both sides, which then forces me to put a 2 in front of the carbonic acid, the HCO3, so we get 2 hydrogen ions and 2 bicarbonate ions. Okay. Now, what we just talked about with precipitation reactions, it looks like we have all aqueous solutions, so this should be a no reaction. But when you put baking soda and acid together, we saw this reaction happen, and we actually formed a gas. We formed carbon dioxide, as we tested for in lab. We didn't use sulfuric acid, but it was an acid, and it did the same thing. So our prediction, as it's written, does not go with the evidence that we saw. And this gets to that second point of other reactions form an aqueous intermediate that then spontaneously decomposes. So what happens is the carbonic acid actually decomposes as soon as it's made because it is more energetically favorable for it to decompose, and it creates water and carbon dioxide. And since I have 2 carbonic acids decomposing, I get 2 waters and 2 carbon dioxide gases. And with carbon dioxide as a gas, we know from experience that it is a gas because of our everyday living, but also it's a small ionic or a small covalent compound, right? The molar mass of that is like 44 grams. per mole. So it also fits under a small covalent compound, which is a gas. So like methane is a small covalent compound, it's a gas, right? And propane is a gas. So, but octane, which is pretty big, right? 8 times 12 for carbon, gets us into like the 100 grams per mole. That starts to be a liquid, okay? So small covalent compound. So this is what we're talking about with the first reaction forms a gas right away. The second reaction, based on our double replacement, doesn't look like there's a gas, but there's a spontaneous decomposition. Okay, so here's breaking this out. When H2S is a product, it is always a gas, and this is something we'll have to get into our brains. And then when the following products are made, they are aqueous intermediates and will decompose. Okay, so we just saw this first one, H2CO3. And then we see H2SO3, which is going to be an aqueous intermediate, and then also NH4OH. Okay, so there's technically 4 products that we're going to see that are going to lead us to think we have gas evolution. And let me switch over to this so we can see what happens. So we said that these are going to be aqueous intermediates and decompose, and we saw that H2CO3 breaks apart into water and carbon dioxide. We see that the H2SO3, which is sulfurous acid, has a similar pattern. We have 2 hydrogens, 3 oxygens, but instead of carbon, we have sulfur. So we can see a pattern here, and we're also going to form water, but instead of carbon dioxide, we're going to form sulfur dioxide. Oopsies. Okay, again, small covalent compound is a gas. And then with NH4OH, this is ammonium hydroxide, which I know technically is a base, but it decomposes spontaneously, that it doesn't actually form a base. It forms a gas and liquid, and all of these decompositions have the same thing in common, water. We're forming water, and then the leftover of water is going to be NH3, which we remember as ammonia. Okay, so those are 3 aqueous intermediates that are going to decompose into gas, and we're noticing patterns. We're not really memorizing a whole bunch into here, but we do need to get this information into our brain about gases. Okay, there's not a lot of them, but it is important because, again, we come back up here and we see 2 aqueous, makes us think no reaction happened, but then when you go into the lab and you do it, you see a reaction, so you need to be able to rectify that in your brain and bring it to fruition and figure out what's being made and why, right? So it's the carbonic acid that is decomposing. Okay, so that's the end of our double replacement types of reactions. In class, we'll have a quick review of this, do some predicting products, and then we will move on to our last type of reaction.